Yeah, there you go. You the man. I got it. All right. Am I got a good picture? You're in charge. Okay. And this is going to be definitions to start with, and then we're going to look at math. The change in the amount with respect to time is directly proportional to the amount present. Now,
Where should we label this? Like for notes?
I'll just leave you a space at the top. We'll get to it. Yeah, I'm going to tell you about 4 different things it's called. And you're right, I'm going to have to do that. But right now, let's just stick with the definition. Okay? But you're right, I got to do that. Okay. If you look at that and you read it, you may not understand some of it. But I hope you do at least understand we're talking about what? Change in the amount is, means equal, right? Proportional to the what? Amount. So the amount that you have affects how fast the amount is changing. All right? Let's use this as an example. I have 4 rabbits in my field. Okay? And in 3 months, I have 12 rabbits in my field. Okay? 0, 3 months. 6 months. 9 months. Okay. I increased by 8 rabbits, right? Am I really going to only increase by 8 rabbits between here and here? Because see, those 4 were able to produce 8, right? These 12, they're going to produce more than 8, aren't they? See what I'm getting at? Yeah. So they may end up making 24. And then those 24 aren't just going to make 12 more. Those 24 may make what? Another 15 or 20, right? Okay? But what we're thinking is that as the amount that we have goes up, how fast the increase is also goes what? Up. Or, I've got 1,000 of something, and then I have 500 of it. I wouldn't put money, but we're not. Then I only have what? 400 of it, 200, 150. But notice how it's going down, and it went down real fast when I had 1,000, right? Didn't go down as fast when I had 500, did it? And then it went down a little bit faster there. That one's a little bit screwed up as far as it's not a perfect example, but you get the idea. What y'all have done so far is lines. When you do a line, the rate of change is constant. Okay? For lines, rate of change is constant. Change in y over change in x. The slope is what? Constant. Well, what we're going to do now is we're looking at changes that are not constant. The changes are based on how much is there at the moment. Now, so you got an idea of what we're talking about, and you've read it in English. The change in the amount with respect to time is directly proportional to the amount present. Well, change in the amount, and notice I didn't use a delta symbol. All right, I used a D instead of a delta. But the D is for delta. That still means what? Change. I'll tell you why. Because over here, we use this when the change is constant. We use this kind of delta when the change is constant. we use this kind of delta when the change is changing. The actual amount of the change is also changing. Is that all right? Okay. Change in the amount with respect to what? Time. DT. Change in time. Respect to. Change in the amount with respect to change in time. Is. Now, when y'all did proportions in the 6th and 7th grade, y'all might have used, one fraction equals the other fraction. What I wish that it taught you is that directly proportional is always a constant of proportionality times the amount. Directly proportional to the what? Amount. So that's your proportional constant, that's your amount. This is the mathematical sentence for that English.
You said the K was the proportion constant?
Yeah, that's the constant of proportionality.
Okay.
And I may be saying that wrong, but it's the constant that you have to multiply by that amount. Because it may not be 1-to-1 proportional. It could be 3 times, 4 times, or just half as much. Okay? Now, this sentence, I'm introducing this sentence to you because this is a Calc 1 sentence. You're going to see this in Calculus 1. All right? You're going to see that sentence. Now, this is called a differential equation. And differential equations are a very big deal. What a differential equation is it's an, how you doing?
I'm alright.
It's an equation based on change. So if you want to write differential equation, is an equation based on change. Y'all have never had that before. All right? You've never had it. This is an equation based on rate of change. It's an equation based on rate of change. All right? And I'm going to go ahead and tell you. How many of you look at all these formulas in your science book and they don't ever tell you where they came from? Yes, you look in your science book, there's all these formulas. Or if you look in an economics book, there's all these formulas in economics books, and they don't tell you where they came from. That's because most of them, if not all of them, came from differential equations. And there's no use in showing you where they came from because you've never had Calc 1 or Calc 2 or this whole class called differential equations. All right? But the whole class, differential equations, is about where those formulas that are in your science book and your chemistry, physics, and all that, where those formulas actually came from. They came from these things. So I just want you to know that these things exist, and they're formulas based on what? Rates of change. Now, through the magic of calculus, is there pixie dust? Pixie sticks, right? They have that powder in them, right? Is that P-I-X-I-E? Mm-hmm. Okay. Pixie dust of calculus, which I can't teach you because you haven't even had differential calculus yet, so I can't teach that. But through the pixie dust of calculus, this turns into this very important formula. The amount at times t is equal to whatever the original amount is, e raised to that k, t. And then when you take calculus, they're going to teach you how to go from here to here. If you look in your college algebra textbook or you look in your pre-calc textbook, they just give you this formula. They don't tell you where it came from at all. They just say, here's the formula. Okay? Here's the definition. This definition is very important because it made this formula, which made what? That formula. And the definition says the change in the amount with respect to time is directly proportional to the amount. Now, there are other types of change. It may say directly proportional to the amount squared. Well, then you'd have to put a 2 here. Then you wouldn't get this. All right? How about inversely proportional? That would put the K over the what? A. You wouldn't get this. All right? So, but that's where it came from. Now, this definition is the definition for what's called natural growth or decay. Natural growth or decay. All right? This is also called exponential growth or decay. Anytime I put the word growth or decay or exponential change, I'm just going to write the word change. It could be growth or decay. Exponential change. It's also known as, in chemistry, chemistry. They have this thing called first order change. Now, here's my problem with chemistry. They have 0 order, first order, second order, third order, fourth order change. I'm almost certain this is the formula for first order, okay? And it may be the one for second order, but this is one of their orders formulas. And I could derive the other ones for you because I know the words up here. But I think this one is first order. You can put a little question mark there, but I think it's first order, okay, in chemistry. But all of these things, natural growth or decay, exponential change, chemistry first order, this is the formula for them. Because the rate of change, the amount of change with respect to time is what? Directly proportional to the what? Amount. If you see those words, directly proportional to the population, directly proportional to the amount, that's your formula, okay? If you see natural growth or decay or exponential change, guess what? That's your formula. Okay. It is also a formula that we can use for half-life. Radioactive decay. I'm trying to write that where the computer can't read it so they won't know I can't spell. Half-life for radioactive decay can also be done with this formula. All right? So you're starting to see this formula is a pretty big deal. If any of your parents are in finance, anyone in here, parents in finance, do a lot of stock market stuff or anything like that, there's a formula called PERT. That they use. The principal is the amount of money you start with. A sub 0, the amount you start with. Principal is the amount of money you what? Start with. The rate is the interest rate, and the T is the number of years. PERT. It's the same as that. So you might want to put that, there are formulas for economics that are involved in this. PERT and that are the same thing. Yeah. All right. Somebody says, Mr. Evans, how do you use the formula? And I will tell you there's some limitations to the formula. Not ready for that yet. Let's just show them how to use the formula. Don't get weird. All right. How do you use the formula? Okay. Well, let me give you an example. Mr. Evans. Found these little things. He discovered a whole new little creature called the math goblet. Goblets are like something that's physical, right? Goblets, math goblets. The MGs, math goblets. Mr. Evans discovered the math goblets, okay? And when he discovered them, there were 10 of them. So A of 0 is equal to 10. When he first found them, there were 10. 3 weeks later, there were 30. He wants to know how many he can expect to have in 6 weeks. He also would like to know how long it's going to take to have 1,000. Because he found out that these little things are really cool and the kids like playing with them on their desk, and he can sell them because they're not really alive. So, you know, they're like just little cells of gook, a little, you know, gook, just a little gobbledygook. What's that stuff that y'all make in science class and play with? Ma'am? Yeah. See? All right, so here's how you would work the problem. You're always going to, for right now, you're going to know a starting amount, and you're going to know some amount along the way, and it's going to have the words natural growth, exponential growth, or something to tell you that it's this formula. Because there's other ones, okay? So let's say it said exponential growth, and it gave you those numbers. Here's how you work it. You write it exactly like I'm about to write it. You don't change it. All right. A equals A sub 0 e to the kt. Well, the catch is A sub 0 is equal to what? 10. Put the 10 in. Don't skip this step. You put the 10 in. Now, use that information and get the 10. Then, you use this information to find k. You've got to find k. This bit of information right here helps you find k. And here's how you do it. You know the amount is what? 30. And you know the time is how much? 3. So 30 equals 10 e to the k times 3. And somebody says, Mr. Evans, you should have written that 3k. And you're like, I should write it 3k, but I'm just trying to show you exactly where I put it. Well, now, just leave it on my desk. We'll get it in a minute. I think everybody here realizes the first thing we can do to solve this is divide by 10. So 3 is equal to e to the 3k. I didn't really want those to both turn out to be 3's. Now, you are going to take the natural log of both sides. You're going to use rule 5. All right? You're going to take the natural log, or rule 4. But you're going to take the natural log of both sides. I'm going to write it out as a separate step.
Is it rule 4 or 5?
It's either 4 or 5. It's the one where you take the natural log of both sides. It's 5. You're going to take the natural log of 3. And on this side, you're going to take the natural log of e to the 3k. What does the natural log of e to the 3k become? Just plain old what? 3k. So we get natural log of 3 is equal to 3k. So k turns out to equal 1/3 of the natural log of 3. That's what k equals. Now, at this point, if you want to put it in a calculator and turn it into a decimal, you have to carry the decimal out 4 places. You don't round off, you don't round up, you don't round down, you just write down 4 decimal places and quit writing anything past that. Fair enough? How many decimal places? 4. If you don't write down at least 4 decimal places, your answer is not going to be that accurate. I'm not going to use any decimal places. I know my k value. So, I have this formula. A equals 10 e to the 1/3 natural log of 3 times the t. And you would have a watt there if you were using your calculator. You'd have a big old watt right there. You'd have a decimal. Okay? Is everybody all right with that? Your K value would be a decimal. I just didn't put it in the calculator. Yes, ma'am?
Can you explain the first to last step and down?
Here?
Yeah.
Okay. I saw the E I needed to get rid of. So I took the natural log of this side because I knew that the natural log of E raised to a power would just be that power. Since I took the natural log of this side, I have to do what? Take the natural log of the other. And then I wanted the K by itself, so I divided this side by 3. Or multiplied by what? 1/3. All right? Now, and like I say, you'd have a decimal there. Mr. Rhodes can't do that. Okay. You now have the formula. This is the general formula right here. You have the formula with the A sub 0 and the K figured out. That's the formula you need to work anything else related to this problem. See how I'm getting it multiple steps? All right. Let's answer this question then. We'll answer the A question. A sub 6 equals question mark. Well, I'm going to put A of 6, and I should, if you wanted to, you could put A with a little set of parentheses with a T in there. Is that okay? A parentheses, but sometimes y'all don't like that. Equals 10 E to the 1/3 natural log of 3 times 6. Does everybody agree that you can take 1/3 of 6 real quick right there? Just multiply. So then you're going to get A of 6 is equal to 10 E to 2 times the natural log of what? 3. And here's where it gets cool if you don't use a calculator. Did y'all remember there's a rule where you can bring that 2 back in here and make it a power? This is the reason if you don't use a calculator, you can still work all this. If you're doing this with decimals in your calculator, you're still going to be good. It's just it's not as easy. Does everybody realize that just equals 9 right there? All of that equals 9? Because that's E to the natural log of something, right? That's the rule. So you'll get 9, so A of 6 equals 9. Okay, so there's 90 little MGs running around in the world. 90 MGs. MG was a cool little British sports car they used to make. MG, great little British sports car. All right. So far, so good? Happy? Now, if you did this with decimals, you'd probably get 89.999. What you need to know is what? 90, or you get 90.001, which is what? 90. All right. Any question about getting the first part done? So who's out here letting y'all smile at them? All these children out here playing now. I don't mind. Y'all can smile at them, wave at them. Throw something at them if you want to. Everybody okay with the first part? Now, the second part, we want to know how long it will take to get 1,000. Okay, how long will it take to get 1,000? There's our A part. See this formula right here? It's key that you can be able to get to that formula. Now, there's our A part. Let's do our B part. Is it going to show up on the screen if I'm over here? All right. B part. I now know that the amount is 1,000 equals 10 E to the 1/3 natural log of 3 times T. I know that the amount is what? 1,000. And I need to solve for what? T. Well, first thing I'm going to do is divide by 10. So I'm going to get 100 is equal to E. And if you don't mind, no, we're not going to do that. E to the 1/3 natural log of 3 times t. Now, I'm going to take the natural log of both sides. All right? Somebody says, no, Mr. Evans, what you could do is, but see that multiplication right there? That's going to mess you up when you try to use a rule. Because you can't do e to the natural log of 3 to the 1/3 right there, because you would have this t out here on the end. Is that okay? So we don't do that. We're just going to take the natural log of both sides. Because that's too complicated. So we're going to get natural log of 100 equals, and it's okay if I put 1/3 natural log of 3 times t, because when I put the natural log here, I'm also going to put the what? Natural log there. Is that okay? Tell me if it's not, because that's hard for me to explain that I'm just going to put a natural log in front, because I know that'll get rid of that e. Is that good? Okay. I need to put a natural log here so that I have natural log of e raised to all of that. If I have natural log of e raised to all of that, it reduces to just that. And then if I put a natural log on this side, I have to do what? Put a natural log on the other side. Now, if you want to, do you see how you have all